Okay. So first of all, I would like to stimulate you to do this pre-exam, those who have not done, just as home task, not put 1.5 hours, just solve as you can solve, yeah? Some of you, some remarks on this home task, now we call it home task. First of all, some of you had a problem to solve such, to expand in Lorentz series. So for example, some function z square az plus b. And this would be typical function on exam, to expand this into Lorentz series. And how to do this, we should find the roots. So for example, z1 and z2 are roots. So then we can write this with some coefficients k1 z minus z1 and plus k2 z minus z2. And what we do, for example, we want to expand at the point z1 in Lorentz series at the point z1. How we do this? This is already the pole of degree 1 in this point. Now we should only expand this function k2 divided z minus z2. So we write it, we should subtract z1 and plus z1, so it is k2. What we are interested z minus z1, and here plus z1 minus z2, and then you should use geometric progression to take this away. No, let us complete this. We can write this k2. To find these coefficients, you just add these fractions, and then would be equations on coefficients. K2, we write z1 minus z2, and here would be 1 plus z, or better is to make minus, yeah? So let us take away z2 minus z1. I think it is correct with signs. Z1, here would be minus z minus z1 divided now z2 minus z1. And now this played the role of denominator of geometric progression, and you can find where it would work, in which area, in which circle around z1 this series converge. Yeah? So this series converge when z minus z1 is less than z2 minus z1. So this is the radius of convergence. And if you want to expand around another point, you do in the same way. Yeah. So this is the simplest way. Of course, you can do this in different ways, but this is the simplest way. Okay. Another thing I did not expect, but in some those who solved, who started to solve home task, no, such things, I think it is just because you did not pay attention. So if I write, for example, sinus z divided by z square, of course, this is the pole of degree 1, because, but some people believe that it's of degree 2 because just here, but we should also look to the order of 0 of nominator, and sinus z is approximately z in nominator. So this function is approximately 1 over z, and this is the pole of degree 1. So when you look to some expression, and for example, see exponent z minus 1 divided by z cubed, so this is pole of degree 2. So look not only to zeros of denominator, but also to zeros of nominator. I think nothing more. Integral over triangles we studied at the beginning of the previous lecture. Okay, so I hope that you will, those who have not yet complete, will complete this home task. because I already put another text with exercises about Fourier series. No, they are not so nice, these exercises, because to expand function in Fourier series, you should calculate integrals, yeah? So integral function multiplied by cosinus nx or sinus nx, and it's very often it's not so nice calculations. In this file, which I put to my model, each exercise has the answer, so you should hope to get this answer. Okay, so look to, I sent you even an email about these new exercises. So what we studied, we take function fx, we ask that it's L2 norm square, so it is integral. Let us consider borrow from minus pi to pi, fx dx is less than infinity. At the previous lecture, we already considered complex Fourier series, so we can consider now f as complex valued. So we can consider L2 complex valued from minus p to pi. So these are functions which satisfy this minus pi to complex values, which satisfy this things hf is less than infinity. So we shall not in future write this C, so functions would be complex valued. Also, in practically all examples, functions would be real valued. And what we proved, that in this space, we can expand our function, if function satisfies, this function is here. We can expand our function, for example, in real Fourier series. So this is some an cosinus nx plus bn sinus nx. And unfortunately, in this book which we use and we shall use today, for example, for proof, no, sometimes people write just a0. Who is a0 in our notations? It is 1 over 2 pi integral ex. So this is the scalar product of function f and function 1 divided by unfortunately, in this book, they write here a0 divided by 2. No, let us use this a0 divided by 2, but then this a0 would have without, for example, it was our a0, then the a0 is equal, or our a0 is the a0 divided by 2. So the a0, it's 1 over 2 pi integral of x dx. So just small notations adjustment, small notation adjustment. So our convergence up to now was in L2 space. So the norm f minus partial sum denoted as Sn goes to 0 and goes to infinity. So up to now we worked with convergence in L2 space, where Sn is just sum up to n. Is 0 divided by 2 plus sum and this is, who is this? This is integral. This is integral, yeah? So this is integral of square of difference. So up to now we studied such convergence in the average meaning when the square of absolute value integrated goes to 0. So f minus Sn, it is integral from minus pi to pi. Here is absolute value x minus Snx square dx, and then go to 0 and go to infinity. And typically in all physical applications, for example, in signal analysis and so on, this convergence is okay. Because as I told, the square of integral, this is energy of signal. And typically they are interested in energy, which is sent by this channel, by this function f. But in pure mathematics, and Fourier series started long ago, so Fourier was at the Napoleon time. I don't know where he was. And moreover, he used this Fourier analysis to improve the quality of French artillery in Napoleon army. I don't know. No, it looks like, because with Fourier series, we can solve heat conduction equation, how artillery work in long regimes. Then he was so famous that Napoleon put him as the Minister of Finance of France. But he was so bad in finances that he was fired maybe in half a year. After this, he was just pure mathematician. He stopped his career. Okay, so, but mathematicians are interested in another story. Mathematicians are interested in such story, and this is also sometimes used for even in applications. When this series, when this function is equal to the series and convergence in point x. So pointwise convergence. Pointwise convergence. So mathematicians are typically interested not when integral, it depends what kind of mathematicians, but those who study real analysis, it was very, very great mathematical science, maybe 100 years ago, which was called analysis of functions of real variable. So this is a part of analysis of functions of real variable. Pointwise convergence. So first of all, we have now two types of convergence. L2 convergence, B, pointwise convergence. Pointwise convergence. They are different. So there is no this arrow, neither this arrow. From L2 convergence does not follow pointwise convergence, and from pointwise convergence does not follow L2 convergence. Let us illustrate by examples. For example, example. Two convergence does not imply pointwise. Now we're in the third part of the course, because course is called Fourier and complex analysis, and also involve a part which is called different types of convergence of functional series. We give the first portion which we need for today. Then we will be back to this. So this is just about convergence of functional sequences or series. How I construct this, for example, a sequence of functions which converge in L2, but not in any point. Even in any, I can construct example when sequence converge in L2, but does not converge in any point. Yeah. So it would be kind of cartoon. We do the following. Take segment 0, 1. So segment 0, 1. And now, first of all, if I take function of such type, so example here, and here is 1, So it is 0 everywhere, but on some segment alpha, beta, it is 1. So this function. And then its integral, that's integral, you know from school, it's area of this rectangle. So if we integral function, this is our function fx, its integral is area. Area. But since this function is equal to 1, even its square, it is area. Even its square, it is area. So this is the normal function. This is the normal function in L2. It is area for such function. Now my idea is the following. I want to construct a sequence of functions such that which are piecewise, which are step functions, 0, step 0. Such that area go to 0, but functions do not go to 0 in any point. But functions do not go to 0 in any point. I think in this book, which we use, there is another example, but there is only one point. And here we want. So I do the following. For example, 1/2. Then it is 1 here and 0 here. The next step. I move this. I will make carton. Yeah. So I move this to another part, and at the same time, move to another part. One step more. So consider this one. So this is first function. This is f2x. Then the next step, I divide this by 4. So this is 1, 4. And this is this function. Also 1. And then I do the following. This go step by step until it's approach 1. So the next would be this one, then the next would be this one. How many we need? And now I approach 1. Then I divide again 2 times. It would be of 1, 4, 0, 1. And here would be, now it's 1, 8. No, it's size. Size here is 1, 8. And then I go this direction. And so I go this, and this. What is my idea? The area is going to 0, because this is going to 0. But sooner or later, it's approach any point. So for any point, it is 0 until this function approach it. Then it's 1. Then it's disappear, it's again 0. Go to another direction. At some step, it's again approach it's 1. Go 0. So in any point, at some number n, function in our sequence equal 1. Then it's again 0. After a few steps, again 1, 0. So fnx does not converge in any point, because it's either 0 or 1, then again it is 0, and again it is 1. But the area goes to 0, so fn go to 0 in L2, but it does not converge pointwise. So this convergence that we studied before in L2 space does not tell us anything about convergence of Fourier series in a point. Does not tell anything about convergence of Fourier series in a point. So it should be totally new theory. How to prove such Fourier series converging concrete points. And we're approaching this theory of convergence in concrete points. But first, I would like to make some remark. Now, if you consider Fourier series, I write just not equal because I don't know whether it's converged or not, but just and coefficients we calculated before is integrals an cosinus nx plus bn sinus nx. We considered first our theory in L2 minus pi. So it is 0 minus pi. For example, our function is such. But now, and before, we were not interested how our functions behave in a point. But now we see that in the right-hand side, we have trigonometric functions, and trigonometric functions are periodic. So cosinus nx plus 2 pi equal cosinus nx, and sinus nx plus 2 pi equal sinus nx. So trigonometric functions are periodic with period 2, with period 2 pi, with period 2 pi. So if we expect that this series converge to this function also should be periodic. So we have to consider periodic functions. Therefore, let us give definition. F is called periodic with period t if for any x shifting to t does not change anything. Fx plus t is equal fx. So function is called periodic. If we shift it to t, nothing happened. But in L2, we did not consider function on the whole real line. Therefore, the only condition when we go to pointwise convergence would be f minus pi equal f pi. But then we can continue our function periodically on the whole real line. So because when we calculate, what is the idea? When we calculate coefficients, we integrate only here. So we are interested in function only here. But this series gives us periodic function on the whole real line. Therefore, when we speak about this pointwise convergence, we take function on minus pi, and then if it is not periodic, we extend it periodically on the whole real line. So plus 5t and so on. So when you study pointwise convergence, you should first of all have this condition. And then if your function was not periodic on the whole real line, forget what it was outside and continue it periodically on the whole real line. So, by hands. And we study now whether the function which is periodic on the whole real line can be expanded in Fourier series which converge in any point. So this is formulation of the problem which was studied in real analysis. Okay. Now we need some remark which would be used later. For example, we integrate some function, some periodic function over segment minus pi pi. So minus pi pi fx dx over period. Now let us make shift and take some point alpha and alpha plus 2 pi. It is somewhere here. No, maybe, no, yeah, somewhere here, maybe. So there's a distance between alpha plus 2 pi. Then it is clear from picture, but you can change, check by change of variables. That if we take integral, this integral is the same as integrate from alpha to alpha 2 pi. Because when we integrate here, it is the whole base. When we integrate here, we have two pieces. This one and this one. So this block is this block, and this block is this block as it was. But of course, you can move to alpha anywhere. So it is equal to integral alpha alpha plus 2 pi fx dx for any alpha. So if function periodic, and you move it to some point, and then take this function on this whole period, integral would not change. Integral would be not changed because of this property. Okay, so this is what we wanted about periodic functions. No. Of course, if function is continuous, we hope to expect, we expect that if we get a good theorem, this series would converge to this function. But very often signals are not continuous, and the typical impulse, the pulse, which people, physicists send by radio and so on, it's a kind of step function. So it is not this nice continuous function, but what typically is sent, it's typically nothing, then they send some signal and again nothing. Yeah. So typically what, example, minus pi, what people are interested, for example, this function. Yeah. This function. So it is not continuous. It was 0, then step, for example, to some value a, and then it's again go down. So we want also convergence, and we can write Fourier series for it. Because function is integrable, it would be just integral over this segment. So we can write Fourier series for such step function. Or more generally, piecewise continuous. So it is, who is piecewise continuous, which is a collection of some functions which are continuous on some segments, and at some points they are singular points. So for example, minus pi piecewise continuous, how it looks? No, for example, it's go here, then jump, it's go here, then jump, it's go here, and so on. And here it's jumps in some points. So piecewise continuous function. And you know the space of piecewise continuous functions by symbol E. Piecewise continuous functions on the segment minus pi. Piecewise continuous functions on the segment minus pi. What is important what we have, for example, for this function or for this function, for example, it is here this, and here is not this, but and here it is, for example, this, and here it is starting here, and it should be periodic, but we can just put it here 0, and in this point also put 0, and it will be periodic. Example. What is important here? That there exists limit from right-hand side and limit from left-hand side. So there exists fx plus 0. So limit delta go to 0 if delta larger than 0 if x plus delta, and if x minus 0, limit again delta go to 0, delta is larger than 0 if x minus delta. So take this limit from this side and limit from this side. Left hand limits and right hand limits. So, for example, in this case, we have such f, for example, this point is x. If x plus 0 is equal to 1, and if x minus 0 from this side is equal to 0. So limits do not coincide generally. If they coincide, function is continuous. If these two limits are the same, then it's just continuous function. And what we can expect from Fourier series, where it would converge in the point which is not point of continuity. So the point where it's jump, for example, it's here was limit fx minus 0, and here is limit fx plus 0. So we have two numbers. And intuition tells us that in this case, of course, one can expect the mean value. So we hope that in this point, Fourier series A0 divided by 2, sum would converge not to fx, because fx is not defined here. It is, no, of course, we can define it here by x, by 0, for example. If, for example, it has, from this side, is defined by 0 in this point, then it jump and starting to again. But it would be naive to expect that it would be 0. So we expect that it would converge to this divided by 2. So this is the main hypothesis. If it's continuous, it converges to fx. If function is continuous, this is precisely fx. So we wanted make such combination from this limit, from right-hand side limit and left-hand side limit, such that when function is continuous, we will get fx. So this is this expression. This expression gives us fx in the case of continuous function. Give us fx in the case of continuous function. So this is more or less what we prepared. Now we need some technical condition. And we're coming to one of the main theorems of the course. It is very long, very technical, but idea is quite simple. What we need more? We also have situations. We won't have such things also for derivative. We want to have such situation when left-hand side derivative exists and left-hand side derivative exists. So maybe the usual derivative does not exist. But left-hand side derivative exists and right-hand side derivative exists. Now, what is the main example of such function? of such function. Function can be even continuous. Take absolute value. So function is even continuous. So there is no jumps. There is no jumps. But if you try to find its derivative from this side, we'll get +1. If you try to find derivative from this side, we'll get -1. So for this function, they exist limit delta t go to 0, fx, or you can write 0 plus delta t, or we write in general case. What is, let us give general definition. What is the left-hand side derivative and right-hand side derivative? D plus fx. It is limit. Only difference is delta t go to 0 and delta t positive. So here you have fx plus delta t. More or less as was before. As was before, but now for derivative. Now for derivative. Minus fx divided by delta t. So we go to x from this side and usual definition of derivative. In the same way, we define derivative from another side. It is the basic example, for example, model x. It has both derivatives, but they are different. X minus delta t minus fx divided by delta t. Okay, okay. So now we are ready to define the class of functions for which we want to prove pointwise convergence of Fourier series, not L2, but pointwise. So define this class. It is denoted, I don't know, we use prime. No, maybe by means of derivatives, yeah? Yeah. So this is pointwise continuous function, so element of this space, such that d plus minus fx exists for any x minus pi pi. Usual derivative maybe not exist. So this is the class of functions. This is the class of functions where we hope to prove that Fourier series converge. It converges to this, not to function f, but just to average of left-hand side limit and right-hand side limit. And right-hand side limit. Okay, so maybe now it's good time to make break, and after break we shall start to prove this very long theorem that if function belongs to this class, if function belongs to this class, then series converge. Then series converge. So break maybe how many? Oh, 10 minutes at least, 10 minutes. 10 minutes break. Maybe I stop recording. Okay, so I did not record this main proof, but it's exist in the book. So those who did not follow lecture, they can read in the book. Yes, I make corrections and will send. So Riemann-Lebesgue lemma. So let f be a function from real line to complex numbers, and it is absolutely integrable function such that integral is less than infinity. Then limit alpha go to infinity integral from minus infinity to infinity fx e alpha x dx is equal to 0. Or let us write here n as in our text. So if we any integrable function multiply by such exponent and n go to infinity, this integral goes to infinity, to 0, is to 0. How to explain this? What happens with this function when n go to infinity? It starts to oscillate very quickly. So and what happens? It's if they spikes up and down. So it's multiply function with positive and negative, positive, negative, and finally there's nothing in this integral. So it's more or less such my intuitive picture. Such this go to 0 because not because this function is small. This function is always equal to 1. So this go to 0 not because something small and put this down. No, this function is not small, but it's fluctuate quicker and quicker. So if you write this graph, its fluctuations become practically every second, yeah, every time unit. How to prove this? No, the complete proof is not easy to do because again we did not have the course in integration theory. We did not have the course of integration theory, but nevertheless, I shall give you main idea of the proof. Main idea of the proof. Idea of the proof. So let fx be a step function. Step function. No, for example, it's again 1. It is 1 on some segment and 0 outside it. So fx equal 1 for x less or equal b, a, and 0, x does not belong a, b. So step function. It is 1 only on segment AB. So of course it's integrable, bounded. So let us prove Riemann-Lebesgue lemma for this function. And it is trivial. It is trivial in fact. Let us prove Riemann-Lebesgue lemma for this function. So integral from minus infinity to plus infinity fx enx dx is integral from a to b enx dx. So we can integrate this function. It would be en b minus en a divided by in. So this is bounded with absolute value less or equals than 1. Absolute value of this is 1. So it go to 0 and go to infinity. Now consider function which is a linear combination of step functions. So, example, we have segments A1, B1, A2, B2, and so on. And our function is step function on each of these segments. Or it's better not use the same variable. For example, x1, x2, and so on. x1, x2, x3, and so on. and it's such steps, and so on. So our function fx is the sum ck. If you multiply this by constant, it still go to 0. So we can multiply each step function by some number as we want. Here from 1 to m, and here is fk x, which is step function on the segment is where fkx equal 1 on the segment xk minus 1 xk, and 0 when x does not belong to this segment. So now consider linear combination of step functions with some coefficients. Because if you multiply this by ck, it still goes to 0. It still goes to 0 independently. It can be any large constant, but it does not play any role. So if you put this into integral, it's clear that each term goes to 0, the sum also goes to 0. So we immediately generalize this. So generalize it. The previous result for step function result to linear combinations of step functions. Riemann-Lebesgue lemma is also valid for any linear combination of step functions with arbitrary coefficients. And now what we miss from the course of integration theory. So this is still very simple. So for one step, we just integrated exponent and got n in denominator. And we use two things. The exponent e is always 1. And then if we integrate, 1 over integral is 1 over n. Goes to 0 and go to infinity. Now we prove this for linear combination of step functions. And what tells us course of integration theory? In fact, such linear combinations approximate any absolutely integrable function. Absolutely integrable function. What does it mean? How they approximate? Approximate in the integral norm. So for any f such integral less than infinity dx, they exist f n, or n is not good here, fm, which is linear combination of step functions such that integral from minus infinity to infinity fx minus such fnx dx is less, for example, 1 over m. Go to 0 and go to infinity. So any absolutely integrable function can be approximated by linear combination of step functions in the sense of integral norm. Those who studied the course of topology is formulated as the space of linear combinations of step functions is dense in L1 space, It's less than infinity. So for any function f, which integral is finite, there exists sequence of linear combinations of step functions that approximate this function in the integral sense. Then we prove Riemann-Lebesgue lemma for this Fm, and then because of this they are so near, we prove this for F. Let us complete the proof. So by using this statement from integration course of integration theory, that any absolutely integrable function can be approximated as good as we want by linear combinations of step functions. So now how to complete the proof? We want now we take any f with this condition and use this So if you write integral from minus infinity to plus infinity fx en x dx, now we subtract such function and add such function. So we write this as fx minus fm x en x dx and plus integral fm x en x dx. Now this we can make small uniformly with respect to n, because if you estimate this first integral, let us denote them E1 plus E2. We know that E1 is less or equal absolute value integral fx minus fmx. And this exponent disappears because it's absolute value 1 dx. Is go to 0 and go to infinity. And the second integral, E2, it goes to 0 for any m, it depends on m. Second integral, of course, depends on m. Go to 0 when n go to infinity. So both integrals go to 0 when n go to infinity. So these things really go to 0. Oh, in fact, we proved Riemann-Lebesgue lemma except this statement that any absolutely integrable function can be approximated as good as we want by linear combination. This is linear combination of step functions. And for step function, integral can be just calculated. So this is finishing the proof of this very long theorem. Okay, so I think it's enough for today. And next lecture I shall try to present this proof just by blocks, as you should. I suspect that it will be this theoretical question. It's for mathematicians. For those who are engineers and physicists, they will get another theoretical questions, not this. I will present this scheme, what you should minimal present at the exam, yeah? Okay, so it's enough for today, and try to go to exercises. There are many exercises, yeah? Now for Fourier analysis, I think 8 examples which I put in new file. 8 examples which I put in new file. Oh,